Swayam Prabha. Digital India. Educated India.
I think this morning is going to look like more, as we say in French, a potpourri. I think it's English also, right? So I want a mix of different things, all related to multi-scale modeling that I will use as a wrap-up. So I'm going to just finish quickly the slides from yesterday, and then I've added a new lecture on the Google Drive, lecture 11 called Wrap-Up Multi-Scale Modeling or something like that, that we will do later on. So this is the slide where we finished yesterday on the nudged elastic band method. Were you all able to get the migration barrier for the vacancy? Yes? Yes? No, I have to do this. Yes? Did you see, so someone in the room, I will not say whom, made me realize that I made a mistake in the energy barrier of the vacancy yesterday. Has anyone noticed that there was something wrong in the barrier that you have computed? No, no one, I mean, except those who have seen it yesterday, no one has had any, doubts or thoughts or reactions with this barrier? No? So actually I made a mistake because the vacancy jumps directly to the second neighbor and not to the first neighbor. So you have the energy that you get, which is actually very high, 2.1 EV. It's much bigger than what it should be. I should have realized, but I in the rush when I did the calculations, in BCC, so this is for iron, right? So it's BCC, so I have an atom in the middle, and then I have atoms on the corner. And then if I take the cell next to it, I have again atoms on the corners, and then there's an atom in the middle. If you can see, you see the atom in the middle? Yeah. So actually, the way the simulation, the NEB was set is that for the initial configuration, you remove one atom and you relax. And then for the final configuration, you take an atom and then you move it to where the vacancy was. And actually, the displacement is either in that direction or that direction, but the displacement is this. So I'm taking the center of the next cell to go in the vacancy. But this is the second neighbor, because where are the first neighbors? At the corners, right? These are the first neighbors of the vacancy. So actually the displacement should have looked like what? So you put the displacement, there's this file displace.txt or something. And inside what I gave you is, there's a number, I forgot which index it is, 210, whatever index it is, and then there's a displacement, which is 2.85, right? Or 80 something 00. So instead of that, what should have been the displacement? An example of, there are many possibilities, there are 8 possibilities, but one of the possibilities could have been?
A by 2, A by 2, A by 2.
Yeah, A by 2. So we could have picked, for example, this atom here, so change the index, and then move it to the center. And then this would be a displacement which would be along 111 or minus 111, one of the 111s. So here it should have been this number divided by, so square root of 3 over 2. So it would have been 1.45 something, and then 1.45, and then 1.45, with maybe some minus somewhere to go in the correct direction. Yes, you see? And if you do it, you get a barrier which would be on the order of 1 EV, probably. Have you done the 0.8 EV? So the correct calculation should give you 0.8 EV instead of 2.1. Okay, so that was for the NEB. And then, so things that we have discussed yesterday, but I think that are important. You should keep in mind that with the NEB, the forces do not derive from the energies, because we only keep a component of both the spring force and the potential forces. So classical minimization algorithms like the conjugate gradient method, which uses the fact that the forces are the derivatives of the energy. They do not work, and that's why it uses a quick min, which is a very inefficient minimization algorithm, but which works here because you only need the forces with a quick min. Then another limitation that you have that you need to have in mind is that for the NEB to work, you need to know in advance both the initial and the final configuration. And the last one is that for these calculations, there are two parameters. The spring constant. In the example yesterday, it's 0.1, but you can put 1 and it will make no difference. So typically 1 EV per angstrom squared. And then the number of replicas. There again, I mean, the more replicas you put, the better the path. Typically, around 20 should be okay. If you have very few images, as in DFT, for example, where usually you would have 4 or 5 images maximum, there's an additional routine that you can use, which is called climbing image NEB, which takes the configuration closest to the maximum and really brings it to the maximum. But this is useful only if you have very few images. If you have like 20 images, it's useless. It will not change anything. Okay. That works. Do you have questions on the NEB? No? Everything is clear? And then we quickly talked about the solid state NEB, where you change the shape of the cell along the path. And this is done by adding springs not only between the atoms, but also between the cell vectors, between the different images. And as I was saying, there are two instances of the method, yeah, so you won't see it, but so this is the initial method, and for the mechanicians in the room, this method works only for small strains because stresses and strains are not conjugate from one another in the way it's explained here. And then there is this other version of the SSNEB where they have properly addressed using the I forgot the second Piola-Kirchhoff stress and the displacement gradient or something. So they used a strain and a stress measure that are conjugated one from one another. Okay, this was for the SSNEB. Now there are cases where you don't know the final state beforehand. The typical case is, so I'm going to jump to here, it's a glass. If you take, if you take an amorphous configuration like this, so imagine that you take an interatomic potential, you start from a liquid, you quench the liquid, your configuration will at some point become arrested, and this will be a glass. So it's a completely disordered structure. So I give you a structure like this one, completely disordered, and I ask you what is the energy barrier to get out of that configuration. So that it's a question that could be related to what will be the time during which the system will be stuck in that particular configuration. How long will it take for the system to go to another metastable configuration? If I ask you that, you're going to have at least two problems. The first one is that the system being completely disordered, you don't know what is the final state beforehand. It's not like a vacancy or a dislocation where you know that the vacancy will go from one atomic position to the next. Right? In a glass, there is no such atomic positions, reference atomic position, so you don't know beforehand what will be the final configuration. And also, you're not going to have just one transition. you're going to have a whole continuous distribution of potential transitions for the system. So you have to do not one energy barrier calculation, but you have to do a whole distribution of, or you have to compute a whole distribution of energy barriers. So to do that, you cannot use the NEB, or it's very difficult. So there are other methods that can be used, and the one I personally like to use, there are different flavors of but it's always the same idea. The one I like to use is called the activation relaxation technique, and it was developed by a guy from Quebec, Normand Mousseau, and then it was improved by people in France like Frédéric Cancès and others, and myself some years ago. So this method is called a single-ended method, because for this method to work, you only need to know the initial configuration, which has to be a local energy minimum in the potential energy landscape of the system. Then so it's just going to be the philosophy. I'm not going to go into the details of the algorithm, but the idea is that starting from this configuration, you pick a direction at random in configuration space. So basically you pick a random displacement for the atoms in the simulation cell. Then you move the configuration along that vector, so you displace all the atoms. And then, so if you do that, the energy is going to go up quite rapidly. So what you do is you look in configuration space at the hyperplane, which is perpendicular to the displacement, and you do a few steps of energy minimization, typically a few steps of quick mean or fire. Not too much, because if you do too many, if you relax too much, then you're always going to stay around the initial configuration. But if you don't do any steps, then your energy is going to go extremely fast, extremely high, and again, there's nothing you can do. So you do typically 5 steps of energy minimization. Now you're in a new configuration, and then when you are there, you compute what is the smallest curvature of the potential energy landscape where you are. So when you start here, all the curvatures are positive because it's a minimum, right? When you go up, the curvatures will change, and so you compute these curvatures. You compute, actually, the only one that is of interest is the smallest curvature. If the smallest curvature is still positive, it means that you are still in the initial basin of attraction of your minimum. So typically, if I go to just one dimension, I'm here, I do a step, then I do some minimization. I'm here, I compute the smallest curvature. If the smallest curvature is still positive, it means that I am still in the initial basin. In that case, I continue moving in exactly the same direction as before. So I do a new step. So I move all the atoms rigidly. I do a few steps of minimization. I'm here. I compute again. It is the minimum eigenvalue is still positive, but it's becoming smaller. I do one more step, still along the same direction, some minimization. I end up here, and here what I find is that the smallest eigenvalue is now negative. Right, so there's a change in the curvature. Here it was all positive. This is the initial basin, and then at some point I start to have a negative eigenvalue here. Once I find a negative eigenvalue, I follow the corresponding eigenvector. So it's going to be a specific displacement, and I do that because there's no mathematical theorem to show it. But in practice, what Normand Mousseau and others have shown is that if I still do finite steps, but now always along the minimum, the eigenvector of minimum eigenvalue. And again, I do some minimization to stay on the line. And in practice, what we have seen is that if I follow that eigenvector step by step, I am progressively going to converge on the saddle point. Once I am at the saddle point, then I can add a perturbation along. So I have an eigenvector at the saddle point, the eigenvector of a negative eigenvalue. I can perturb the system along that vector both backwards and do a new energy minimization to make sure that I am still connected with the initial configuration. And then I add a perturbation in the opposite direction and I do an energy minimization, and that will give me the final configuration. You see the idea? Now, this is in 1 dimensions. In 3n dimensions, reality is much, much more complicated. So there are many cases where once you arrive here, so sometimes you just never find an activated state. Sometimes when you do the minimization, actually you realize that you've gone over a valley without realizing it, and so you are no longer connected with the initial configuration. A lot of things can go wrong in these calculations. But if you spend the time needed for it to work, so there are many numerical parameters involved in this method, like the size of these steps here, the number of energy minimizations there, etc., etc., etc. Just when the first time I got interested in this, I was on sabbatical, so it was good because I had all the time of my life. But I spent a whole month just tuning the parameters of that method. So NEB does not, you can pick the parameters of NEB, there's no problem. With this, the most difficult part is to tune the parameters. And one of the main issues that we have with this method is that when we present it, so I can present it like this, when Normand or other people present the method, usually, they will show, oh no, yeah, sorry, I forgot to say. So the nice thing with this method is that now I have found one saddle point. Now I go back to the initial configuration. I pick another direction at random, I pick another initial direction at random. I do the same, and I might find a second saddle point. I go back again, and then I pick a third random direction. I might find a third, etc., etc., etc. And if I do that, I can sample locally the potential energy landscape around an equilibrium configuration, and I can get this distribution of activation barriers. I know for a big enough glass that I will never be able to get all the transitions, and it's hidden here, but there's a line here saying that at least I can sample enough activated states to have a representative distribution. And then I can draw distributions of activation energies, and I can say things. I know that the distribution of activation energies will converge after a few thousand activated states. So that's basically what we have done. Yes?
So the idea here was to find the nearest next minimum.
So you can be interested with the next minimum, or if you want to compute a distribution of activation barriers to know how long you will stay here, what is most important is the activation energy here. But with this method, you get both. You get both the new energy here, and you get the activation barrier.
Plus sample.
And then you sample around to get, so you have this one, and then maybe there's one here, and then you might have one here, and then you might have one there, etc., etc. Yes. So the eigenvalue is just one number, right? But then you need to know in which direction to go along that negative eigenvalue, and that's the eigenvector that tells you what is the direction associated with the negative eigenvalue. So as long as all the curvatures are positive, you go along the initial random direction. This is to get, so you pick a direction at random, and then you walk along that direction to get out of the basin. And once you are out of the basin, then you follow the minimum eigenvector, the eigenvector of minimum eigenvalue. Just to say that if you are interested, because we're interested only in the lowest eigenvalue, we don't need to diagonalize the dynamical matrix at every step, which would be crazy computationally expensive. There are algorithms, and so in particular there's this Langchos algorithm that will give you an estimate just of the lowest eigenvalue. And it's an iterative algorithm, but which converges rather fast. So that's what we use for the negative eigenvalue. Then we follow, and then we relax. Okay. So what I was saying is that when you look at, if you ever see people talking about these methods, when they present them, usually, they will show you some glorious picture of the Alps or something, saying, you start in a nice small Swiss or village here, and then you go up like this, and then you go up like that, and or no, this is the summit, so it would be here. You go up like this, and then you go up like that, and you end up at the saddle point in a nice call on a very nice day and so on. Reality is actually this. You're walking in a big fog, you see nothing, and you hope that you're not going to fall. Because what is happening is, in practice, what is happening is not going like this, as I showed. It happens when you have a very simple potential energy landscape. In reality, what happens is that very often, not very often, always in practice, when you find the first negative eigenvalue, you are actually very high in energy. And then when you are following the eigenvector, actually you are following a ridge. And in complete darkness, because you only know so it's as if with your feet, you were feeling just where is the local curvature, and then you make a step, and then you feel, and you're blind, and you feel, and then you make another step, and it's super easy to fall either on one side or on the other side of the ridge. So there are many cases where you go up, and then you start to follow the eigenvalue. You see that your energy decreases, and then you see that it decreases, and at some point, the lowest eigenvalue is again positive. So you're back in the basin of attraction, or either this configuration or another one. I've spent months with students trying to find ways to go back to the ridge and go down. We never found anything that really worked. The most efficient way is if you go back with a positive eigenvalue, actually you forgot this search, you go back here, and you take another random direction, and you do it again and again and again and again. In the best case scenario, the best we were able to get was about 30% success. So yeah, 2 out of 3 times, you try and you fail, you go back, and only once in 3 times you get it right. So it's painful. It's really painful. But what is interesting is that now if you apply it to a glass, these are the kind of things that you can draw. So for example, it's a very simple Lennard-Jones potential, only 4,000 atoms. And in practice, what we have found is that if you have as many saddles as the number of atoms, the distributions are converged or close to converged. And so here you have, it's a bit messy, but you have 4 different distributions. So these are distributions of activation energies from one given configuration, and the configuration was obtained by cooling a liquid at different quench rates. And so all of this is normalized. These are Lennard-Jones units, so there's nothing physical about it. But this quench rate here, which is the fastest, it's very fast even on MD timescale. It's like 10,000 MD steps to go from the liquid directly to the glass. So this is a glass, the blue one is a glass which was quenched extremely rapidly even on MD timescale. And then we quench 10 times slower, then 10 times slower, then 10 times slower. This here would be on the order of what everybody does in the field to produce glasses. And so what you see, the most important part is here. What you see is that when you quench a glass very rapidly, there are many saddles with a very low activation barrier. So it means that if I draw the usual picture of glasses, I have a liquid which is at very high temperature, so this would be the energy. And then I do a quench. If I do a very rapid quench, I'm going to fall in a configuration which is only barely stable, in the sense that it's going to be surrounded by very low activation energies. And this is what you see here. For the very rapidly quenched glass, I have a large fraction of very low activation energies, almost down to 0. But then as I quench the glass more and more slowly, it means that I'm going to, instead of finishing here, I'm going to finish at a lower energy and in a configuration which will be more stable and surrounded by higher activation energies. And because, so if it's higher activation energies, it's because you have less and less of these very low activation energies. They are always there. But you have less and less of them because the system is better and better relaxed, meaning that it's going to stay in that configuration longer and longer. Slow. Yeah, oh, there's something wrong here. Yeah, you're right, you're right. Blue is very, very fast. So wait a minute. It's a quench rate. So this is a big quench rate. This is a small quench rate. No, it's fine. So this is a quench rate. So it's like Kelvin per seconds. And so I'm decreasing by. So if these were ones, I would be decreasing at 2 Kelvin per second, and here I'm decreasing at 2 10 to the minus 3 Kelvin per second. So this is the fast quench rate, and this is the slow quench rate. No? Does it make sense? So the units, forget about the units are Lennard-Jones units, both of energy and time and blah blah. So it would be, yeah, the quench rate would be Kelvin per second. They are Lennard-Jones units. In truth, that would be on the order of 10 to the 7 Kelvin per second. If I was using real units, that would be about 10 to the 7 Kelvin per second. So that would be 10 to the 8, 10 to the 9, and that would be on the order of 10 to the 10 Kelvin per second. So even our lowest quench rate is humongous compared to experimental quench rates. What does that mean for these distributions? If I was able to quench my glass at an experimental quench rate, what can we expect for this distribution? So you'll have large energy barriers. So for this distribution, what would that mean? What would happen to the distribution? So in this region here, there would be nothing left. Okay, no low barriers here, and basically this bell-like structure, bell-like distribution here. What would happen to it? It would be shifted towards higher energies. There would always be some very low, because there are always some atoms that are can move, can do back and forth flips, like the so-called two-level systems. So these will always be here, but there will be very few of them compared to all of the other energy barriers. So our level of knowledge in crystals is much higher than in glasses. So in crystals in particular, we are helped because we have a reference configuration. For amorphous systems, we don't have a reference configuration, so we cannot prepare a well-relaxed glass because we don't know what it looks like. So we do what we can with what we have. All numerical glasses, so some progress has been done these past few years mixing swap Monte Carlo and molecular dynamics. It works very well, but for very specific interatomic potentials, not these binary systems here. So for binary systems or ternary systems, realistic glasses, we are still doing these quenches very fast, which means that the glasses that we have in our computers are always far less relaxed than real glasses. So we cannot make any prediction of kinetics, for example. They will be extremely accelerated in our computer compared to experiments because we start from glasses that are very, very badly relaxed. So they still evolve very, very rapidly on human timescales. So we cannot make quantitative predictions, which means also that we don't care about the interatomic potential. Since the structure is going to be crap, then you can use a Lennard-Jones potential, and you might as well use a Lennard-Jones potential. For me, it does not make much sense to use ab initio calculations on a glass, because so you represent very precisely the interactions, but on a structure that has nothing to do with the experiments. So, I mean, you can do, I mean, some people do, but you have to be extremely careful with what you say about what you get from your simulations. In my case, and that's something I loved when I started looking at glasses, is that I don't care about the potential. I can just, get away with a very simple inner Jones potential and still say meaningful things, because in glasses, there are still very fundamental phenomenological questions. In particular in metals, we are at a stage where we expect the simulations to give you quantitative data. Not in glasses. We're far from that in glasses. Yes, yeah. So it's difficult to know. Usually what people say is that in a metallic glass where there are no strong bonds, the number of saddles increases exponentially with the number of atoms. In systems where you have strong bonds like silica, the network glasses, then it's closer to linear, but it is still so big that we'll never be able to get all the saddles. So, sorry, say it again. So here, this is not silica, right? This is an inner Jones potential, so that would be a model for a metallic glass. So this is the kind of system where the phase space increases exponentially. This is not silica. I have equivalent curves for silica, but even if a priori, because it's very difficult to count them, but even if a priori the number of saddles increases less than exponentially, the initial number is already so large that even in silica you're not going to be able to get all of the saddles. So the time scales of the MD simulation are too fast to have diffusive rearrangements. There is a little, but not that much. There is some short-range order that might occur. It's really more that as the atoms are cooling from the liquid, if you cool them slowly, they will have time to rearrange and find energetically favorable configurations. So in particular, what has been shown, it's not true for this potential, if I remember, but for many other potentials, what you see is that when you have, so let me remember, it's the big atom tends to be surrounded by, so it's going to be hard to draw on the board, but tends to be surrounded by an icosahedra of first neighbors. No, actually it works also, no, I remember, it works also for this one. One way to measure in the structure what is the level of relaxation is to count the number of big atoms surrounded by an icosahedra of first neighbors. That number increases with the relaxation of the glass. So the lower the quench rate, the higher the number of icosahedra, for example. But it remains an approximate measure of the structure, but it works quite well. Yeah. So that would be the first step, right? That's what I was about to say. So among the multi-scale methods, there are multi-scale methods in time, where you stay at the atomic scale, but you try to expand the time scale from the MD time scale to human time scales. One way to do it is to use kinetic Monte Carlo. And are you all familiar with the basics of kinetic Monte Carlo? So the idea is that it's a way to say, if I have for example, I'm here and I have two states here. I know that my system is going to vibrate around that minimum until at some point it's going to go above either that barrier or that barrier. And I know that the probability to go above this barrier will be proportional to exponential minus delta E1 over KT. And the probability to go above this one is exponential minus delta E2 over KT. And I know that the characteristic time to go above this one will be proportional to exponential plus this. The characteristic time to go above this one will be plus. Kinetic Monte Carlo is a way to select which of the two the system will go above and how long it's going to take to go above this barrier. So it allows you to have a physical time. So you no longer model all the vibrations as you do in MD. You only go above the energy barriers, and kinetic Monte Carlo will give you what is the characteristic time scale that it would take to go above this barrier, and then when you are here, you do it again. And then here, and then you do it again and again and again. So the issue here is that to do properly kinetic Monte Carlo, you would need to know all the barriers, and you never know all the barriers. So we tried to. So that was my initial aim, and that's how I got money, because this was fancy. I'm going to do kinetic Monte Carlo in glasses, blah blah blah. We never were able to make it work. We tried the tricks starting from the energy distributions to pick elements in that distribution. It never really worked. The main issue was that we don't know enough energy barriers to have a realistic time. So maybe for those who know these methods, and who know Sidney Yip, some years ago he proposed a method called ABC method. So the ABC method, it doesn't work at all, because it gives you, in principle, only it should give you, in principle, if it works, it gives you the smallest eigenvalue, energy barrier. It gives you none of the others. And so you can get a time scale with that, but it's completely wrong. Anyway, so that was my my remark with CD. Anyway, other questions on that, or?
How do you choose the random directions in that?
I use a random number generator, and okay. I can use a random number generator to
if it is
pick.
normal distribution, it will be around some.
Yeah, so in practice, what works best is that in the configuration, at random, I pick one atom at random among all the atoms, and then at random, I pick displacement along X, along Y, and along Z to form a displacement vector for that atom. And I use that random vector here as my initial displacement. So initially, I only move one atom. But then as I minimize the energy and look for the eigenvalues, the eigenvector of minimum eigenvalues will involve the displacement of many atoms around that initial atom. Do I make sense? And so the displacement, when I go back, I'm going to pick another atom, and I'm going to pick another displacement. When I go back, I'm going to pick another atom and another displacement. When I go back, I pick another atom and another displacement, etc., etc.
So how do you come up with those particular directions only?
Random. I pick the displacements it's a random sphere. So the amplitude of the displacement is fixed. It's one of the parameters, and I pick the direction at random on the sphere of that displacement. Yes.
We can't use normal distribution.
You can. It's not going to make much difference. Honestly, it's not going to make much difference. Yes. So there's. I will mention it at the very end, but so there's exactly what we have said. So using these energy barriers obtained with art plus kinetic Monte Carlo. There's a method available which is coupled with the lamps, so you can use it in lamps, and it's called kinetic art, so kinetic activation relaxation technique. And it works, but in simple systems where you can sample enough of the states. And it's what I'm going to say at the end is that for what I know, most, if not all, multi-scale methods, they work, but on simple systems. Tracking complex, realistic system with multi-scale methods is today still very difficult. So kinetic art works. It works in crystals, for example. If you want to look at the migration of a vacancy, for example, you take a high entropy alloy, you put a vacancy, and you want to know how it will diffuse. Kinetic art will work because at every step you have only 8 barriers to find. Even you can do NEB in this case because you know with which atoms the vacancy will change. But if you take a grain boundary, for example, you put a vacancy in a grain boundary and you want to look how the vacancy will move in the grain boundary, kinetic art will work because there are few barriers for the vacancy to move. But for glasses, forget about it. That's the worst you can do. Okay, Okay, so now I want to move on to this new lecture. I had initially thought I would tell you about solid solution strengthening, but I think what I'm going to say here will be of interest to more of you than solid solution strengthening. So, yes. So I want to talk about multi-scale modeling. No, actually what I can do is, as a matter of introduction, sorry, I'm going to skip a few slides and then I'm going to go back to it. When you do multi-scale modeling in our community, at least some years back, you could not give a talk without showing what is called the multi-scale phase diagram. I'm sure you have already seen it. I mean, this is part of our contract. You give a talk in modeling, you have to show the multi-scale phase diagram. So this one, I took it from Dirk Rabe. It's a bit different from the usual one because he has put the length scales here and the time scales there. Usually it's the other way around, but it doesn't change much. And then he has put here the usual succession of simulation methods. Ab initio at the bottom here, and then you have dislocation dynamics here, then you have, molecular dynamics here, then you have here dislocation dynamics, and then you have crystal plasticity, and then you have finite elements. Okay, I'm sure you have all seen this. Now, actually what I find interesting is that there are different ways to move in, two things that I want to say. The first is, if you look at the number of decades that you have here in length, you have about 9 orders of magnitude, right? If you look in time, you go from 10 to the minus 15 to 10 to the 3 or more. So actually, the multi-scaling in time spans many more decades than the multi-scaling in length. And this is very often underestimated. So actually, there is a huge challenge here, even you remaining at the atomic scale, but doing multi-scale in time. So in this case, you are not moving. So most usually, especially when you use method where you fit parameters of a model from simulations at the scale below, and you do it again and again. This is called sequential methods. And when you do these sequential methods, most often you move diagonally in the phase diagram. But you could also move vertically, where you stay at basically 0 temperature, or there's no time, but then you try to change the space scale. And these are the methods usually, they are called concurrent methods, and that's, for example, I'm going to say a few words at the end, but quasi-continuum or CAD or QMMM, all these methods, they work at 0 temperature. So you're down here in time scale, but you go up in length scale, or at least that's what they try to sell. But then you have other methods where you stay at the atomic scale, but you increase the time scale. And this is typically the kinetic Monte Carlo method that we just talked about. We stay at the atomic scale, but we are trying to get thermally activated time scales. And there are other methods like the accelerated molecular dynamics method, PAREP or TAD or others. I'm going to say a little word. What I wanted to say is that keep in mind that there are different ways to move along the diagram. I'm going to show examples of a sequential, maybe not method, but a methodology or approach. And actually, we're going to move, how are we going to move? We're going to move mostly in this direction, actually. Even if it's sequential, it's not really like this, it's more like this, which is the thing I've been mostly doing in this realm. And the example I want to take is, we're going to go back to dislocations, and we're going to go back to my favorite BCC screw dislocation. And I'm going to show you what we have done to try and get a dislocation mobility law that you can use in DD simulations, for example, directly from DFT calculations. And then this is not really multi-scale, but it's a fun study, so I thought I would maybe tell you about quickly about HTP metals, and I know that among you many are interested in HTP metals. Just a quick acknowledgement. So all of this was done with a bunch of people with whom I've been collaborating for a long time. So people at CEA, so the nuclear agency near Paris, Emmanuel Clouet, Lisa Ventelon, François Willem, and Lucille Deserald is a former PhD student from my group who is now an assistant professor. Okay, so these are the two examples I want to talk about. So what is the mobility law? So the mobility law would be this function here, which would be a function of, in principle, the applied stress tensor, the full tensor, and the temperature. And that function gives you what is the velocity, the corresponding velocity for a dislocation segment, right? And this mobility law is at the basis of all the dislocation dynamics simulations, because you use the dislocation dynamics to tell you what is the local stress tensor, you know the temperature, you get the velocity, and then basically you move the segments according to that velocity, and then you do it, you recompute the stresses, and you do it all over again. Now, if you want to have a velocity law like this for a BCC metal, this law should incorporate what we call in the community of very often the surprising feature of BCC. So first of all, it should account for the fact that the velocity is thermally activated, and there's a King-pair mechanism. Second, that depending on the stress and the temperature, the mobility of the dislocation can be limited either by the nucleation of the double kink or by its propagation or diffusion along the dislocation line, or if you're at high stresses, as we have discussed yesterday, it could also be limited by how the dislocation interacts with the phonons, how it can dissipate the vibrational energy. So you need to account for that. And then there's something which is very specific to BCC metals. It's the so-called non-Schmidt effects. So just to illustrate what they are, we've already said it several times during the week. So we have this Schmidt law that says that the plasticity is controlled only by the component of the stress tensor that creates a shear along the Burgers vector in the glide plane. And we know that this is typical of FCC metals. BCC do not follow this law, and this is known almost since the same time as the Schmidt law, 4 years later. And there are two reasons why the BCC metals do not follow Schmidt law. The first one is the so-called twinning, anti-twinning asymmetry. The idea is that imagine that the dislocation is moving on this red plane here, and I am applying a maximum resolved shear stress on the blue plane here. If only the projection of the stress on the red plane counts, as is assumed with Schmidt law, then whether the blue plane makes a positive chi angle, like this, or a negative chi angle, like that, we should have the same resolved shear stress, because it's the same projection, right? You do it in FCC, it works fine. You do it in BCC, this is an experimental example. This is if you are applying the resolved shear stress right on the 110 slip plane of the dislocations. This is if you apply it at 30 degrees. This is if you apply it at minus 30 degrees. This difference here is called the twinning, anti-twinning asymmetry. And then there's a second non-Schmidt effect, which is due to the fact that not only the resolved shear stress matters, but basically all of the terms of the stress tensor affect the mobility of the dislocation, even if they don't create a driving force, and they are called non-glide effects. Right? So now, there have been works in the past to develop velocity laws. In my opinion, the most advanced model was developed by Giacomo Po and many others, including Jaime Marian. And this is the law that they came up with. So you have, this is the velocity, and you have two regimes depending on whether there is a king pair formation, a positive barrier for king pair formation or not. So if there is a barrier, then you see we find again this exponential minus delta G over KT that we have talked about yesterday. And there's here a mobility coefficient. And then if you are in the athermal regime, so if the barrier is 0 or negative, then you are limited by phonons, so you are now proportional to the applied stress, and there's still a mobility term here. And the mobility term itself depends on whether there is a barrier or not. So this law here, it accounts for the thermal activation. It accounts for the transition between thermal and athermal glide. And it also accounts for the non-Schmidt effects through the expression of the free energy barrier. And so for that, what they did, it's very typical. You will see it in many papers. You start by looking at the activation enthalpy. And you assume that the activation enthalpy follows what we call Koch's law, where you have a ratio of the actual stress divided by what would be the pile stress. And then it's a nonlinear function with two exponents, P and Q. Okay, so you take this shape for the activation enthalpy. Then you need to worry about the activation entropy. And there again, you have two choices. Classical choices. Either you assume that the activation entropy is just a constant and it does not vary. It's a constant, so you can put it in the attempt frequency. Or what some people have done is that they have assumed that the entropy follows the so-called Mayer-Neldel law that says that the activation entropy should be proportional to the activation enthalpy. Again, this is an empirical law that has been observed in different systems. So you can pick one or the other. Here, what they have done is they have picked this one. They have assumed that the entropy is constant. Second. Then third, you need to put in the non-Schmidt effect. So far here, there's no non-Schmidt effect. To put in the non-Schmidt effect, the critical resolved shear stress here, you have what is called a generalized yield criterion that was initially proposed by Vašek, Vitek, and co-workers. And we know that because of Vitek's idea was that the non-Schmidt effects are coming from the fact that the resolved shear stress to move the dislocation does not depend only on the resolved shear stress, but it depends also on the stresses that are resolved in the other 110 planes of the structure. And he said, or him and forgot his first name, Bassani and others, what they said is that let's do something that is done often in mechanics, which is let's do a linear combination. Say if the overall stress depends on different terms, let's do a linear combination of these different terms. And let's say that the dislocation will glide when this linear combination arrives at a critical value. And so here you introduce phenomenological parameters, this tau here, this A3, A2, there's a A1 hidden here. And there are other parameters, right? There's this, so H0, P, Q, T0, that's about it. So you have a number of parameters. Now, these parameters, you can get them either by comparing with experiments or with MD or atomistic simulations. But you should keep in mind that the first law, Koch's law, this is phenomenological. The second, Mayer-Neldel law, it is phenomenological. The third law that is used is also phenomenological. So everything, I mean, they make sense. I mean, they make sense, but there's no physical ground to justify these laws. And also, and this is something that really should have been stressed out by Vitek and the others. This law here, as it is written here, it only works for uniaxial stresses. It does not work for any stress tensors. And I've seen way too many papers where people have used this law not in uniaxial traction, but in full finite element calculations. And this is wrong. This is physically wrong. Anyway, so starting from this, the questions that we had when we did this work were, for example, why does a linear combination here can be used? And actually, it works very well. So why does a linear combination works so well? Also, can I predict the different terms from atomistic simulations? In particular, can I predict this A3, A2, A1 directly from atomistic simulations? And then, and I won't have time to talk about it today, but there are also questions about this. Should we take a constant activation entropy, or should we take Mayer-Neldel's rule or something else? So to answer these questions, what we did is what we like to do. So we do DFT. We take a small cell. We put a dipole of screw dislocations to have periodic boundary conditions in all directions. And then we correct for the elastic interactions between the dislocations to remove this artifact from the energies. And then we run the calculations. What we mostly do, So we run the calculations just as a general knowledge. What we know in these, or in the BCC crystals, is that there are different very highly symmetrical position for the screw dislocation. The screw dislocation can be centered on, so for this orientation, on a downward triangle, or on an upward triangle, or it can be centered very near an atomic column, or it can be the saddle point for along the Peierls barrier when the dislocation is moving from one configuration to the other. Right? So there are different positions for the dislocation. What we did to try and characterize the energy of the dislocation is we used the energy elastic band method to look at how the dislocation moves from one easy core to the next, but also to go from the split core to the hard core. So we computed the energy along these two lines, and this is the kind of result that we obtained. So going from easy to easy, this is the Peierls barrier that we have talked about a lot of time. Now going from split to hard, this is something that we haven't talked about. This is the kind of energy that we get. So what we see is that the hard core, the one that is stabilized by carbon, in pure BCC metal, this hard core is an energy maximum. And actually, the split core is an even higher energy maximum. And side remark, you have to keep in mind that many of the interatomic potentials would predict that this split core actually is an energy minimum, like the famous Mendeleev potential. Mendeleev potential says that the split core is metastable, which is not in agreement with DFT calculations. Anyway, from these two energy lines, here and here, using splines, we can reconstruct a two-dimensional energy landscape for where the dislocation is. And now, when the dislocation is moving from one easy core to the next, it's going to follow a trajectory along in this potential energy landscape. Now, in this orientation here, this is the 110 glide plane. When the dislocation goes from easy to easy, on average, it goes in this direction. But what we have seen by looking at where the core of the dislocation goes along the NEB path, actually what we have seen is that the path is very, there's only one case where the path is really linear, it's iron. In all other systems, the path will be deviated towards the split core, always. And this is because if you look here at the energy along the ridge here, actually the minimum, if it was completely straight, then the minimum would be in the middle. But since the split and the hard core are not symmetrical, there's no reason why the minimum would be in the middle. Actually, the minimum is always shifted towards the split core as is shown here. Why do I mention that? I mention that because, so these are calculations that Lucille did when she was a PhD student. So this is the So I'm sorry, with respect to the slide before, now it's reversed. So the split core is here, the hard core is there, and these are the two easy core configurations. This is in molybdenum, and this is the trajectory that the core follows when the dislocation goes from one easy core to the next core. This is aluminum, and this is niobium. So what you see is that the trajectory, except for iron, if you look at niobium and molybdenum, the trajectory is deviated, and the amplitude of the deviation depends on the material. 0 in iron, intermediate in molybdenum, very large in niobium. And so looking at these trajectories, and this is really Lucille's insight, she said, when you apply Schmidt law, you say that all that counts is the stress which is projected onto the glide plane. So here it would be the 110 glide plane. But what we see is that in reality, the glide plane is 110, but only on average, because there are these deviations. And what she said is that let's assume that actually what counts is the stress which is resolved not on the 110, but along the trajectory which is deviated. And so to make things simple, what we said is that we're going to assume that the trajectory, the deviation here is linear, and so we can define an angle here, alpha, which is the angle of deviation of the trajectory. You see what I mean? And then what we said is that, so instead of projecting along this line, we're going to project along that line here, so which would be the 110 in the case of iron, but which would be strongly deviated in niobium, and then with an intermediate angle in molybdenum. And so it means, in practice, that if you apply Schmidt law, what counts is only this chi angle that I mentioned before. Remember, for the non-Schmidt effect, I talked about this chi angle here. If you apply Schmidt law, it's only the chi angle appears. If you apply this modified Schmidt law that Lucille proposed, well, you have the chi angle, but now you have to add this alpha angle that depends on the material. You see, so this would be applying Schmidt law. This would be applying the modified Schmidt law. The only difference is this alpha angle. But now from that, what we can do is we can try and predict what is the yield stress as a function of the chi angle. So if I'm using Schmidt law, I'm going to get something which is symmetrical because everything depends only on chi with a cosine. When we do the experiments, this is the result of the yield stress as a function of chi. This is in molybdenum, this is in iron, and this is in niobium, all in black. The prediction from our very simple law with the alpha angle coming from DFT directly, no fitting parameter, just alpha is coming from DFT. What you see is that it's not exact, right? But qualitatively, we recover that iron actually is almost symmetrical. Niobium is somewhat asymmetrical. Sorry, molybdenum is somewhat asymmetrical, and niobium is very strongly asymmetrical, twinning, anti-twinning, and that's just because of the angles. So actually, iron is almost symmetrical because the alpha angle is almost 0. This is intermediate. This is large. And so with experiments, the comparison is always difficult. So what we did is we did really painful brute force DFT calculations to measure the pile stress as a function of the chi angle in molybdenum and tungsten. And so the dots, the symbols here are the painful DFT calculations, and the black curves here are the prediction, no fitting parameter. And you see that the agreement is perfect in molybdenum. Good in tungsten, there are some deviations, but still, I think, rather convincing that it works. You see, yeah? If I'm going too fast, stop me, right? Slow me down, and I'm fine by... Are you good? Can you follow more or less? Yeah. That's the that's the mean question. We have tried to find a correlation between this alpha angle and other properties like elastic anisotropy. We don't know what controls the value of the alpha angle. So we don't have a theory that can link this alpha angle to other properties of the material. Was that your question? Yeah. Are there other questions? No, you're good. And so, cherry on the cake. Actually, if you just use a simple trigonometry, you can rearrange this term in something that is completely equivalent to Vitek's law for the twinning anti-twinning part, and with an A1 parameter, except that now we have an expression for the A1 parameter as a function of the alpha angle. So now A1, in this way of writing the yield criterion, A1 is no longer a fitting parameter or a phenomenological parameter. It is a consequence, a direct consequence of the alpha angle that we can measure on DFT. Okay? So that was for the twinning anti-twinning part. Now we have the non-Schmidt effects that we have already talked about. So the idea is, we said it yesterday, for example, here we apply a pure shear on the dislocation, and we look at its Peierls barrier and how it is affected by the pure shear, and we see that there is indeed an effect, which is this non-glide effect. And our idea has been to model, as we said yesterday, we're going to model the core of the dislocation as an Eshelby inclusion, a cylindrical Eshelby inclusion, with a given surface here and a given eigenstrain tensor. Right? And then, yeah, what we these are maybe, this is probably too detailed, but in the what we said yesterday is that there will be an effect on the barrier if not only there is an eigenstrain, but also if the eigenstrain varies along the path. But indeed, in the initial configuration, when the dislocation is in its easy core position, because of the threefold symmetry of the crystal, the eigenstrain tensor has to be diagonal, and the XX and YY terms have to be the same because of the symmetry, and they might be different from the ZZ term, but the two are the same. When you start moving along the path, then you have broken the symmetry, and so actually the stress tensor can have other non-diagonal terms. So XX and ZZ no longer need to be the same. There might be diagonal terms, and in practice, there are only two that become non-zero. The others, we checked that, we cannot prove it, but we checked with the simulations that these two other terms remain always zero. So now we have 1, 2, 3, we have 4 different eigenstrain terms. Is there a question or? No, you're good? And if we accept that we have such eigenstrain tensor, how is this eigenstrain tensor coupled with the applied stress? If I know the eigenstrain tensor, how can I predict the effect on the energy barrier within elasticity? I know that if I have an eigenstrain tensor and then I apply a stress tensor on top of it, then the bias on the energy will be times the stress tensor double contracted with the difference in eigenstrains between the initial and the configuration where I am, right? So I can rewrite the enthalpy. This is the full shape of the enthalpy of the dislocation. There is the Peierls stress when there is no applied stress whatsoever on the dislocation and when the dislocation is moving along 110. Then here there is the bias due to the resolved shear stress that will depend on the alpha angle because the resolved shear stress is computed on the glide plane. And then there's here the coupling between the applied stress tensor and the core eigenstrains. Now I know that, so this would be the enthalpy along the full path. Now I know that the activation barrier is where the enthalpy is maximum, so it corresponds to the derivative of this function equal to 0. And you can also show that when the barrier disappears, when I am at the pile stress, when the barrier disappears, then you have both the first and second derivative of the enthalpy that have to be 0. So you do some math. You take the first derivative, second derivative. You look at when both are 0. And then you play a bit with the calculations. And then you have to do some approximations. But to first order in the stress tensor, you can show that the condition to be at the pile stress is written like so. So you have a term here times the resolved shear stress plus a sum over the elements of the stress tensor times the derivative of the eigenvalues equal a constant. This is exactly the same phenomenological form as Vitex form. This is a linear combination of terms from the stress tensor with weights. Here, there's one here, equal to a critical value, which is here. Except that now, none of these terms are fitting parameters. We can predict them directly from DFT. So we have removed the phenomenology in doing this. All the different terms, we get them directly from DFT. You see what I'm doing? Yeah, so I've said it. So this is same linear combination as the initial criterion. It is valid for all stress tensors, not just for uniaxial traction, because here we had to make no assumption about the stress tensor. All the terms of the stress tensor are here, so it's valid for any stress tensor. And it's physically justified both for the twinning, anti-twinning, which is here, and the non-glide. Now, does it work? So comparison between DFT and that model. This is where we are safe, and it works extremely well. These are pile stresses as a function of the chi angle. These points here are the DFT, again, very painful calculations. These are calculations of the pile stress for different chi angle and different pure shear deformations. And the lines here, they're not fit. These are predictions from our model. And you see how well it works. But this is where we are safe. But still very happy to see that it works so well. Yes, and so yeah, so that was what I wanted to say about this generalized yield criterion. We have also worked on the entropy. I don't think I want to go into the details. We've used one of these thermodynamical integration methods to compute directly the Gibbs energy along the piles barrier. And from the Gibbs energy, taking the derivative with respect to temperature, we can get the entropy. But I don't want to go into this. I just want to say that after all that, what we have tried to put. Oh, I didn't put the. No, it's hidden here. So there's a paper that we have done with Emmanuel 3 years back, where we have tried to do the exercise of really going from the DFT calculations all the way to comparing with experimental measurements of the yield stress as a function of temperature. And the result is not disappointing, but not great either, in my opinion. Oops, sorry. No, it's going to come, yes. So there was a question of which slip system will be so we had experiments here where they reported that so these were tractions along a direction in the triangle which is here. So we had a lot of information about these experiments. The thing is, if depending on the slip system that we assume is activated, in one case we get something which is really off, in another case we get something which is a bit better, but the prediction also depends on, there's one unknown parameter which is the dislocation density. So there's more, an area of prediction which encloses all the experimental points. But we have to make also an assumption on what is the activated slip system. That information we didn't have. So
You mentioned that you generate whole curve using ab initio. How did you get the dislocation density?
how do we? So this area here is by predicting the yield stress and assuming different dislocation densities. We couldn't measure them, so we took numbers. So we start, and actually, we start at, so here it's 10 to the 7 per meter square. This is 10 to the 16 per meter square.
Found using the Taylor's relation.
Yes, it's in there. Yeah, it's in there. Everything is in there, but there are still parameters that we do not know. But there's, I don't know if you, maybe it's too small, but there's one caveat here, or there's a trick that we have played. A huge trick. I mean, because it doesn't look that bad, except that there's une arnaque, as we say in French. I'm completely fooling you in how I compare with the experiments. What is written here? What is written here? What is the scale here? What is the scale here? It's not the same scale. So to have the comparison, we had to rescale our predictions to be in the same range as the experiments. Why is that? So this is something well known in our community. We've been talking about the pile stress predicted by interatomic potentials. That pile stress systematically is 2 to 3 times larger than the experimental value. Always, whether you are using interatomic potentials or you are using DFT, the pile stress predicted by atomistic simulations for the BCC dislocation is 2 to 3 times bigger than the experimental value. Why is that? Different groups have different ideas. Some years back, we proposed that it was related to a quantum effect in the motion of the atoms. Because since the pile stress is measured at very low temperatures, there might be an effect of the 0-point vibrations of the atoms. We have shown that it is plausible with an EEM potential. People don't agree with us. People have done DFT showing that that what we have might be just because we're using EEM potentials and not DFT. So there's still a discussion in the community about why the atomistic simulations are so wrong. Now that's something that you should keep in mind. If you try to do materials design for BCC metals from the atomic scale and sell it to industry, your points will be 3 times too big. So that might be hard to sell. but we don't know why. We don't know why our simulations are. So this scale here is okay comparing these simulations and experiments. This scale is wrong by a factor of 3.